Hello, this is Otsochi Odemba, and today we'll be solving a problem 5 of the 2018 NMC exam. And in this problem, we are asked to show that this expression here is a perfect square. So how can we go about this? You agree with me that that is really very complicated and not something we can work with directly. So we may or we should look for ways on how to make things a little simpler that enable us show that is a perfect square. Maybe look at how we can actually factor some squares out, right? And to do that, let's take a look at generally, each of these terms are in the form of 2 raised to the power of 6 minus 1 over 2 raised to the power of 2 minus 1, 2 raised to the power of 6 minus 1. So each of those terms are in that form, some 2 raised to the power of 6 minus 1 over that 2 raised to the power of 2 minus 1. So we might want to look at that and see if there's something we can get from there. So let's look at x raised to the power of 6 minus 1 over x raised to the power of 2 minus 1. This is just generally a general case, right, for all the terms in that product there. So of course, if we want to do difference of squares for both the numerator and denominator, we can do that. So let's say this is x cubed squared minus 1 over x squared minus 1. And that gives us x cubed minus 1 times x cubed plus 1 over x minus 1 times x plus 1. So this is still not friendly. So you may want to break this down further, right? So to do that, we can use the difference of cubes and the sum of cubes formula. And that's basically saying that the one for difference of cubes says that a cubed minus b cubed is equal to a minus b times a squared plus ab plus b squared. And the one for sum of cubes says a cubed plus b cubed is equal to a plus b times a squared minus ab plus b squared. Can actually confirm either of this and they are true with just common expanding the bracket, right? So they are known formulas. So let's use that. Of course, this is 1 cubed, 1 cubed. So we can use that for the numerator. And that gives us s cubed minus 1 cubed gives us x minus 1 times x squared plus x times 1 is x. Then, of course, 1 squared is 1. Then times x cubed plus 1 cubed will give us x plus 1 plus x squared plus x times 1 is x. And 1 squared is 1. And, of course, we still have over x minus 1 times x plus 1, which can cancel out to give us x squared plus x plus 1 times x squared. This is minus, sorry. Times x squared minus x plus 1. Right, so let's continue working with that here. Now, this is a little bit more friendly, or maybe is the friendly we are looking for, because now we can express if you express each of these terms in this form, there are no more denominators involved. So it's easier to bring out squares than this, than when things are canceling out on that you don't know what cancels out, like what you don't know, whether if they are denominators, you can comfortably bring out squares because you feel like some things or some more things will still cancel out. So with this, we can comfortably bring out squares if we express everything in this form. So basically, we are looking at something like this, 2 squared minus, let's take the minus part first because it's smaller. So we'll have 2 squared minus 2 plus 1 times 2 squared plus 2 plus 1 times 3 squared minus 3 plus 1, then 3 squared plus 3 plus 1, then all the way, right? Then we'll keep on going all the way, 4 squared plus 4, 4 squared minus 4 rather, 4 squared minus 4 plus 1 times 4 squared plus 4 plus 1, right? And then it keeps on going up to 22 22 squared minus 22 plus 1, like that. So basically this is still not it's not what you are looking for, right? But at this point, let's just test it out and see. Now that the denominators are out, you can easily test out and actually see what you are looking at and how this may actually result to being a perfect square. So let's try that out. 2 squared minus 2 squared is 4 minus 2. That's 2 plus 1. So we have 3 here. 2 squared 4 plus 2 plus 1. Now give us 7, right? And of course the multiplications. 3 squared is 9 minus 3, 6 plus 1, 7. 3 squared is 9 plus 3, 12 plus 1, 13. 4 squared is 16 minus 4, 12 plus 1, 13. At this point, you are suspecting something, right? This is not looking like it's a coincidence. But let's try out one more and see if it's actually something we want to look at. So, okay, let's take 4 squared, 16 plus 4, 20 plus 1, 21. And of course, the next term is going to be 5 squared minus 5 plus 1. And 25 minus 5 is 20 plus 1 is 21. So it looks like this pattern is going to keep on repeating, right? So it's something that we want to look out. And it's something that is we are actually happy, right? Because at this point, we know that this can come out as a square. This can come out as a square. And we can comfortably bring out all these squares, right? Because if we bring them out, there it doesn't really change the what you're working with. If it's a perfect square, it's going to remain a perfect square, and if it's not, it won't. So you can comfortably bring out all these squares, right? Which was actually the aim from the beginning, like I said, but we couldn't do it because of the denominators. Now you have seen this pattern, we just need to prove it, and by proving it, it makes a what you're working with a lot easier, because at that point we only need to look at 2 squared minus 2 plus 1 times 22 squared plus 22 plus 1. We only need to look at this to confirm whatever we are confirming. So, okay, let's actually try to prove this. So basically, to prove this, we just have to show that a squared plus a plus 1 is equal to a plus 1 squared minus a plus 1 plus 1, right? And we can do this very easily, right? So a plus 1 squared minus a plus 1 plus 1 is equal to a squared plus 2a plus 1, then minus a minus 1 plus 1. And of course, that simplifies to a squared plus a plus 1, which was what we wanted. So I've actually proven that, and that tells us that these couples will keep on going, right? These couples will keep on going. And we can comfortably bring out a square, right? Because it doesn't change the result. For example, 32 is not a square, right? And no matter if you bring out a square from 32, for example, 4, the remainder is going to be 8. 8 doesn't change from being a square, right? That comes from the prime factorization. So we can keep on bringing as many squares as we like, and it's not going to change our final results. So like I said, at this point, all we just need to check for is 2 squared minus 2 plus 1 and 22 squared plus 22 plus 1. So 2 squared is So we just need to check for this, like I said. So let's do that. So 2 squared minus 2 plus 1 and 22 squared plus 22 plus 1. If this is a perfect square, then we are done. Is equal to 2 squared is 4 minus 2 is or let me just write it out. 4 minus 2 plus 1 and 22 squared is 484. Yes, plus 22 plus 1, right? And then that's equal to, let me scroll down a bit. That's 4 minus 2 is 2 plus 1, 3. Then 484 plus 22 is 506 plus 1 is 507. So we just need to check if 3 times 507 is a square. And then we can easily do that from the prime factorization of 507. Right? So this is 3. 507 is 3 times 169, which is 13 times 13. And of course, this is a square, right? Is going to be equal to 3 times 13 squared. And we are done. If this is a square, then the whole expression is a square, and that solves this problem. So that'll be the end of today's video. Thank you, everyone. See you in the next video.